Okay, here we go. The Tacoma Narrows Bridge collapse.
What meter?
And the wind begins to speak with a roar that no man can fail to hear.
Why is it moving like that?
The feather span leaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now.
Why is that on?
The 11,000-ton feather span slips and swings the giant cables as support. Cables of 6,300 wire strands, each 17 inches thick. Back out of the danger zone, all stricken spectators are driven to safety as the bridge gyrates like a nightmare high along the river, twisting, turning, curving.
These are channels is
The lone motorist is forced to land on the tower. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance.
There's a car
Will
in
he
there?
keep the last warning or perish with the doomed structure? But he saved himself by seconds.
Now, do you guys know why he was out there?
He must be suicidal.
And his little Poochie dog was in the car. And he couldn't get the dog out of the car. He's like, I don't think it was his dog, it was someone's dog was in the car. And so he's like there trying to coax the dog to him, and the dog cowered and wouldn't go to him. So, one of the reasons.
Oh, who got that dog by his car?
The dog's in the car.
No structure of steel and concrete can stand such a flame. Steel girders buckle and giant cables snap like shooting threads. There it goes!
There we go. It's about time.
Those are some awful engineers.
Gavin, that was 1940.
Those are some awful engineers.
Disaster, some claim it was the use of solid girders, others differ. But whatever the reason, the Como will rebuild. This time a bridge that will not provide a super thrill in the news.
Those are the same engineers that build planes.
10 best bridge collapse.
Alrighty, turn the light on. Somebody.
Or was it a compilation?
So, the point of, oh, did you turn that on? Oh, you have it on right now. Oh, cool. So did they, yeah. So they showed that as part of the lesson. That'll be fun. So the point, oh, could you turn one of the lights off? Thanks, Sahara. Cool. Thank you, Sahara. It's fun to order Sahara around. Now, could you do other stuff for me, Sahara? Okay, the point of today's lessons is resonance. What was happening with that bridge was a very small periodic force. They talked about 40-mile-an-hour gale winds. Well, 40 mile an hour isn't that much. We get much worse here in Rancho Cucamonga. It's not the wind. It was the fact that the bridge was resonating. The fact that a small periodic force was creating a huge amplitude of oscillation. And that's what I'm going to teach you today about resonance and how you get resonance and stuff like that. So here we go. Get this. Wait. Because I need room for myself for the whiteboard. Okay, here we are. Alrighty, here we go. I'm gonna make a spring mass system here, just a second. Okay, great. Here's my mass. I'm going to exert a force with my hand. I'm going to exert a periodic force, and I'm going to make this mass go up and down with an incredibly high amplitude. Are you guys ready? Incredibly high amplitude. Here it comes. Look at how much force I'm exerting. Look how much my hand is moving. My hand is moving inches. How much amplitude am I getting?
Not a lot.
None. Well, maybe if I exert more force, how much amplitude of oscillation am I getting?
Barely.
Oh, so what am I doing wrong? I'm exerting a periodic force. Why am I not getting a big amplitude of oscillation?
You're exerting the force on the top of the spring, not the mass.
Okay, but I can still obtain that. I'm just asking you, I need to change my force. Yeah, Logan.
Because the period of your movement is not the same as its period.
Okay, tell me more. Let's talk in terms of frequency. What would you like me to do with the frequency at which I'm imposing the force? How many people say increase it? How many people say decrease it? Yeah, good for you guys. And then we'll get what Logan is talking about, where the period of my imposed force is going to match the natural period of oscillation of the spring mass system. But we don't use period when we're engineers. We tend to use frequency. So here we go. I am now going to slowly lower the frequency of oscillation. Are you guys okay? Am I getting my big amplitude now?
Yes,
Sure. Oops. That was not supposed to happen.
I know.
Okay, so one thing I want you to see now is how much force am I having to exert? Here, watch my hand. Okay, how much force am I exerting to get this big amplitude of oscillation? Am I exerting as much force as I was before?
Nope.
Not at all. My hand is barely moving. And yet my hand is barely moving and I'm getting a huge amplitude of oscillation. Okay? Well, there's a name for what I'm doing here. It's called resonance. I am creating resonance. I'm causing the spring mass system to resonate. I'm exerting a small periodic force and creating a large I just don't want the people downstairs to get irritated. Well, thanks, Pooja. Thank you. And I'm creating a large amplitude of oscillation, and that's what what resonance is. Here we go. Resonance, a small periodic force creates or causes. Maybe I'll say causes. I don't know. Causes a large amplitude of oscillation. That's resonance. Now, you'll notice I had to lower my frequency until I found the right frequency. So I found it kind of just through trial and error. I lowered my frequency until I got there. But without me exerting a force with my hand, I could have been able to observe what the natural frequency of the spring mass system was. What could I have done? Is there something I can do so I can look at it and go, oh, that's the frequency with which I should exert my force? Is anyone thinking, put it into oscillation? Is anyone thinking, hey, just bang on it? Look at that. I bang on it, or I displace it. And do you see that frequency of oscillation? The frequency of oscillation that it naturally has when you give it a displacement? Okay, we call that the natural frequency. And that's the frequency with which my small periodic force must act. Okay, at the natural frequency of the system. Okay. Okay. Force must act. Whoops. At the natural frequency or resonant frequency. Those are both synonyms of the system. And then I get resonance. Let me give you another example of a resonance. Here's my glass, okay? Oh, it's not working. Huh. There we go. How many people have done that sort of thing before? Okay, good. Good for you. Tell me, my glass, does it have to be crystal or will it work with any stemmed glass?
Has to be crystal.
No, actually any stemmed glass. Any stemmed glass will do it. Doesn't have to be crystal. I see a lot of kids not wanting to do it because they figure, oh, this glass isn't crystal. Well, don't let that stop you. You can do it with any stemmed glass. Now, why does the glass have to be stemmed? Why couldn't I just do it with a glass like this? Say again? Please.
Like, okay, it won't keep going. Like, you kind of stop the, like, vibrations of it.
Thank you. I'm stopping the vibrations of it. My big fat hand is going to stop the vibrations of it, right? It would be like if someone had a spring mass system and then did that and said, okay, go ahead and resonate it. Well, you know, my big mitt is there hanging on. So yeah, you just need to have your hand be isolated from the system so it can freely vibrate, okay? So now those of you who've experienced this, tell me, if I add water, does the frequency go up or down?
Up.
How many people say the frequency goes up if I add more water?
Sure.
Higher frequency. Okay, how many people say the frequency goes down when I add water? Okay, a few more of you. Okay, well, let's look at the spring mass system. Okay, here's the natural frequency of my 500 grams. What if I add 1 kilogram to it? So now it looks like this. What have I just done? By adding more mass, what have I just done to the natural frequency of the system? Here, I'll put it. Has the natural frequency gone up or down? Yeah, down. And in fact, sometimes as an engineer, you want to put more mass on a system. If you feel, ooh, I don't like the resonant frequency being at that frequency, I like the resonant frequency to be lower, then you add more mass and you can drive down the resonant frequency. That's the sort of thing. I wonder if that happened on the Tacoma Narrows Bridge. I don't know if you listened to the announcer, but he says people don't know why it happened. Maybe it was because they used solid girders. And you know, they use solid girders instead of girders with holes in them, because usually you want to use girders with holes in them because they're lighter, but they're not going to be as strong. And so they use solid girders because they're stronger, but they're heavier. So maybe they thought it drove the resonant frequency down in some way. But my understanding is they used solid girders in the first place because the sucker was vibrating. So they said, uh-oh, we better use solid girders instead of the whole girders with holes in them. Oh, but getting back to this. So in light of what I showed you with the spring mass system, do you think the frequency is going to go up or down? How many people say frequency goes up if I add water? How many people say frequency goes down if I add water? Yeah, let's find out. Here. Keep that in your mind. Is that a lower or higher frequency?
Lower.
Good. Some of you have good musical sense. So you guys okay that when I add water, the frequency goes down? When I take away water, okay, you guys okay with that? Okay. Alrighty. Let me see. Next thing, bottle of water. Here, I'm gonna get this water out of there. Okay, here we go. Empty bottle. Now, I'm going to add water. Is the natural frequency, the frequency you hear, is it going to go up or down when I add water? Is it going to go down like it did with the glass? Because with the glass, what was vibrating? Yeah, the glass. The glass itself was vibrating. What's vibrating here? What's that? No, not the water, because there is no water in here, at least not too much. Yeah, the air. This is an air column that's vibrating. This is a tube. Tell me, is this a tube open at both ends, or closed at one end? Yeah, closed at one end, but it's a tube nonetheless. So it's the air that's vibrating. It's the air that's put into resonance. So when I add water, what's going to happen to the frequency? It's going to go up or down. Who's thinking up? Okay, why? Why is the frequency going to go up? Because what's happening to the wavelength of my vibrating air column? Yeah, it's getting shorter. And if the wavelength of the vibrating air column is getting shorter, then the frequency is going to go up. You guys okay with that? If I add a little bit more water? And add even more water. You guys okay with that? As I add more water, the wavelength gets smaller, which means the frequency goes up. Okay, and as I get rid of the water, the wavelength goes down. Okay, great. Hey, let me show you this. This is a big metal bar, okay? What's one way I can get the resonant frequency of this? We saw with a spring mass system, if I hit the mass and made it go up and down, whatever frequency it naturally vibrated at, that was the natural frequency. How am I going to get the natural frequency of this guy? Yes, Anais? Sure, tap it on something. How about drop it on the floor? Okay, I'm going to drop it on the floor, and I want you to listen because you're going to hear a clang, but then after the clang dies out, you may hear a higher pitched frequency of vibration. So I might go clang, zee, you know, like that sort of thing. Here, please listen. Here, I'll drop it from here. Yeah, let's drop it from here. Well, I didn't hear it that time. Let's try it again. Let's try it again. Well, I can hear the high frequencies, but that's because I'm looking for them. Okay, here, I'm going to make this thing vibrate myself. So you heard, you know, that clang, that's the natural frequency. Okay, so this is kind of what the bar is doing. It's vibrating, and the entire length, you know, that's the first harmonic of this bar when I drop it on the floor. But now I'm going to do something interesting. I'm going to hold the bar here at the very center, and I'm going to excite vibrations on the bar. And I'm not going to excite vibrations by just dropping it. I'm actually going to rub my fingers on it in the same way that I have to rub the lip of this glass. And I'm going to talk about the meaning of that momentarily. But here, okay, I got to put resin on my fingers because I need a lot of friction. Okay, here we go. Now, remember how it sounds? You know, that sound is the first harmonic.
Oh, that's crazy.
Okay, you guys okay with that? This is the, tell me, I'm grasping it in the center. Why does this sound so much higher? Go ahead, Fatima. Okay, tell me, yeah, specifically, what have I done?
You shorten the wavelength.
Okay, good, shorten the wavelength. Thank you. What I've done is actually impose a node right there. By my fingers being there, I'm imposing a node. So now, I'm not getting the first harmonic anymore. I'm getting the second harmonic, okay? And this mode of vibration, actually it's not a transverse mode of vibration. You can tell because I can tap it and it doesn't go away. Here, let me show you. This is actually a longitudinal mode of vibration, but the same thing applies. Here. Do you notice I'm tapping it and it's not going away? You know, the vibration's not going away because the vibration is longitudinal. If I want to make it go away, here, I got to tap the bottom. See what I mean? So it's a longitudinal mode of vibration, but still the same thing applies. I'm imposing a node at the center. Okay, what if I impose a node 1/4 of the way down? Which harmonic am I getting now if I impose a node 1/4 of the way down? Which harmonic is that? Here. I'm going to impose a node right there, 1/4 of the way down. So which harmonic is that? Yeah, fourth harmonic. Excellent. So let's go ahead and do that. Here we go. Oh, shoot. I'm not able to do it very well because it kind of hurts after a while. Shoot, I did it great earlier today. Can you hear that? Oh, okay, there we go. You guys okay with that? Fourth harmonic. Yeah. Higher than the third harmonic. Doppler effect.
He's gonna throw this.
Are you hearing it at all? Is there a Doppler effect happening? Good enough. I don't know if the video is going to pick it up, but there you go. Okay, great. Here's the next thing I need to talk about. I want to talk more about harmonics on things, but I want to talk now about this small periodic force, okay? When I had this spring and this mass, okay, then the frequency of that small periodic force was around 1 hertz. So it was very easy for me to exert a force at that frequency. But what happens if the resonant frequency is hundreds of hertz, like here on this glass, you know? I'm obviously not exerting a force exclusively of 300 or 400 or 500 hertz, whatever this is vibrating at. I'm obviously not doing that, but I'm still getting it to resonate, okay? And the reason I'm able to do that, and I'm just going to tell you right now, I'm not going to try to squeeze the answer out of you, is by me rubbing on the lip of the glass and by doing that friction thing where I get bonds and break bonds and make bonds and break bonds, okay? The frequency at which I'm doing that is incredibly high, and it's many, many different frequencies at the same time. Okay, I'm imposing not just a force at a frequency like I do with the spring mass system. I'm exerting an infinite number of incredibly small forces on an infinite number of frequencies, except only in a range of frequencies. So if the frequency if the resonant frequency of this glass happened to be 400 hertz, then of the infinity of frequencies of vibration that I'm imposing, one of them has to be 400 hertz. And then what will happen is the glass essentially ignores all the other frequencies of force, but resonates at the 400. Among the infinity of forces I'm exerting, it resonates at 400. Okay, does that make sense to you? I don't have to specifically impose the force at the natural frequency. I can impose an infinity of forces at an infinity of frequencies, and as long as one of those frequencies is the resonant frequency, then I'm going to get resonance. Well, one example of this is the clarinet. Does anyone in this class play a reed instrument? Okay, good. So tell me, Alfred, what do you play? Clarinet. And what do you play, Paul? Okay, good. So tell me, right here, my finger is imposing the periodic force. When you play the clarinet, what's vibrating? Here, I'm making the lip vibrate, my fingers vibrating. What's vibrate when you play the clarinet? Yeah, the reed. But tell me, I've never played a clarinet before. Could I step right up, stick that clarinet in my mouth and start playing? Yeah, it won't be good, because what happens is, in order for you to create the range of frequencies of vibration for that reed, what do you have to have? What do you do? What's the name for how you orient your mouth? Yeah, embouchure. You need the correct embouchure. You need to orient your mouth and lips in such a way that when you blow on the reed, you get that reed vibrating within a range of frequencies that includes the frequency you want to play, right? If you're going to play a 256 hertz C on your clarinet, then that reed, among the infinity of frequencies that, I better talk quieter, among the infinity of frequencies that reed is vibrating, one of them better be 256, or you're going to sound like me playing my son's clarinet, where I get no sound. I just blow and nothing happens. And that's because I'm not making the reed vibrate at 256. I might be making it vibrate at other frequencies, but not 256, and so I'm not going to get that sound. You see what I mean? So, let me ask another question. Does anyone here play a trumpet? Okay, well, you guys are probably aware. Tell me, With a clarinet, it's the reed that's vibrating. With a trumpet, what's vibrating? Yeah, the lips. And so let's say I want to play a really high note on the trumpet. Then how are my lips going to, a high frequency note, how are my lips going to have to vibrate? What's that?
Really fast.
Yeah, really fast. You're going to have to tighten up. You're going to have to blow, I mean, you got to really make those lips, vibrate quickly so that you can get a high enough frequency of vibration with your lips that matches the resonant frequency of the air column that you're trying to excite. You see? By the way, people who play the trumpet, how are their lips oriented? I'm sorry, not the trumpet. People who play the tuba, how is a tuba player's lips oriented? Yeah, go ahead, Paul. What's that? Yeah. Yeah. I mean, they're playing incredibly low frequencies, which means their lips have to vibrate at low frequencies. You see? Now, there's another way to make something vibrate besides imposing frequencies of vibrations of the reed and the glass or whatever. You can just bang on something. Just hit it with a hammer. Okay? Like this glass. Remember this? Well, there's a way I could have predicted that this would be the resonant frequency. Just snap it. Okay, and that's because when you exert a large force over a very, very small amount of time, when you exert a force that's looking like that, if this is a graph of force versus time, okay, then it turns out that that force has all of the frequencies of vibrations there are, at least within a range. And so that's why I knew I could get the resonant frequency of this guy, not just by using my rosin, but by just dropping it on the floor. Because when I drop it on the floor, I'm imposing an infinity of frequencies of force on it, because that's what you do when you bang on something. And among them, it would resonate at the frequency that is its natural frequency. But in order for you to hear the higher harmonics, I either had to get lucky when I dropped it, or I had to do the rosin thing. And by the way, that's why I need the rosin. I'm vibrating this thing at thousands of hertz, which means my fingers have to vibrate against this bar at thousands of hertz. And the only way that's going to happen is if I rosin up my fingers. Does anyone here play the violin? Okay, tell me, your bow. You got to make sure that your bow does the same thing that my fingers do, right? So what do you have to do to the bow?
I have to take the rosin and rub it against the bow.
Right, you got to rosin up the bow in the same way I rosined up my fingers, because you need your bow to be sticky, so it will give you that friction and give you those the frequencies of vibration. Okay, great. Let me show you something else. This is a guitar. It's a single string guitar. It was made by a student of mine named Stephen Flores. It was many years ago. Everything here was made by hand, including the pickups. He actually took, motor wire and wound it around, and has the magnets in the back, or the magnets right back there, and that's it. He made a pickup. Everything here he made by hand, except for a couple of the switches that he bought commercially. Okay, let me turn this on. So you guys, okay, you can hear that note, right? But I got some problems with feedback now. This thing is so old. Okay, but here's what I'm going to do. I'm going to put my finger on the 12th fret. I'm going to put my finger on the 12th fret and lightly touch the string, and then pluck the string and remove my finger. Okay? How many people have played the guitar and done that sort of thing? Okay, so you know what I'm going to do. I'm going to make what's called a harmonic. That's what we guitar players actually call it. So here we go, Okay. But when I put my finger there, so what am I doing when I make that harmonic?
Imposing a node.
What's that?
Imposing a node.
Yeah, I'm imposing a node. I'm imposing a node in the center of the string. And so I'm getting the second harmonic. You see? You guys okay with that? Now, you don't have to just make the second harmonic. You can make the third harmonic. again, I need to put my finger on the string, but then remove it right after I pluck so that it just remains a note. Okay, and then we got one. There we go. And I should be able to get one here. Oh, here we go. Can you hear that a little? Yeah. So, you know, these frets are drawn on. These aren't actual frets. They're just his estimate of where the frets should go. So I have to kind of use my ear to get where the... Okay. Those are the harmonics that you get from a guitar. Let me see what else I was gonna do. Oh, here's one. Yeah, here's one. Here's my slide whistle. Okay. You notice this end is closed. So is this a tube closed at both ends? Or where's the opening for my slide whistle? Yeah, right there. And this is the way a recorder works. If you're a little kid, if you're a little 6-year-old and you want to make music, but you're not going to be able to develop an embouchure to play a reed instrument or a brass instrument, then you get a recorder. And what they do is you blow into this little slit, and then the air gets all turbulent inside that slit, and then the air that comes out ends up having all the frequencies. And then among those frequencies, one of them will be the resonant frequency of this air column, and then a little kid gets to play notes. Does anyone here actually play the recorder a little seriously? Okay, then how do I have to change my breath to get the lowest notes on my recorder?
You have to reduce it like a lot, barely blow into it.
Thank you. You got to reduce it a lot. Barely blow into it. Yeah, because if you blow normal, you're just imposing nothing but high frequencies and not enough of the lower frequency forces, and your air column's not going to resonate. You know, or it'll sound high pitched when you want it to sound low. Yeah. Okay. So here's the slide whistle. Oh, by the way, when I pull this thing out, is the sound going to get lower pitched or higher pitched? Higher pitched? Because remember, this is the air column right there.
Lower or higher.
Okay, well, here we go. You guys okay with that? So it gets lower pitched. Why does it get lower pitched? What's that? What's that?
There's more length to it.
Yeah, more length, which means what am I increasing?
Wavelength.
Yeah, wavelength. A bigger wavelength, lower frequency. Great.
Wavelength frequency different.
Okay, great. Here's the second to last thing I'm going to show you, because I'm pretty much done. You've learned everything I have to teach you about resonance. Here's a bunch of bars. Unfortunately for the teacher under me, I'm going to be dropping all these bars on the floor. So tell me, which bar is the high frequency bar? The big bar or the small bar? Good, small bar. Why? Yeah, smaller wavelength. Excellent, smaller wavelength. So let's go for it.
Sure.
Here, I'm going to do them in order.
So he's roughing a xylophone.
Okay, here we go. You ready? Here it comes. Are you ready for the thing? Okay, here we go.
That was pretty cool.
Love them bars.
We should do pretend music. Distract. Just find a computer.
I'm telling you.
Yeah, I could play a song as long as I used each note once. So it'd be a 7-note song.
No, let's find like a
Wait,
big
should be an
bucket.
8-note song. Oh, there it is. Alrighty. And then finally, this was a project that a student made, Daniel Chavez and Catherine Chua in 2009. I have them write their names. You'll be doing projects at the end of this year. And so, here's your glockenspiel. Okay. All right. So Resonance. I don't think I have anything more to say about it. Just remember what resonance is. Remember what the natural frequency is. If any of you become engineers, you don't want anything you build of a structural nature to have a resonant frequency in the real world. You can have imaginary resonant frequencies, but you can't have real resonant frequencies because that's really bad. All right, then bye.